Okay, thank you. Very good afternoon to everyone. So I am going to speak about Earth origin and evolution. When we say evolution, we have to begin with the origin of Earth and how it evolved over a period of time and how it is today. So we have to see the entire history of the planet. If you see, the Earth is the most active planet in the inner solar system, and is the largest planet also in the inner solar system. The here. And the activity inside this planet also caused the surface and interior changes. That's what we see in terms of evolution. If you look at the smaller bodies like Moon, Mars, and Mercury, they are very small. Because they are very small planets, they cooled very fastly. And they become one plate planets. So because they became very inactive very long ago, they preserved the world heavily cratered surface like this. Therefore, the small planets contain evidences of geological processes that affected these planets about the first half of the solar system history. On the other hand, if you look at the large planets like Earth and Venus, they are very different. They are active since for a long time because of the heat engine remains active. Therefore, they destroyed the world history. If we want to understand Earth, also Venus, we have to look at the Mars, Mercury, and Moon, look at their surface so that we understand the first 1 billion years of our own planet. The Earth is located here. It's a third planet from Sun, and it is placed between Venus and Mars. It is located in a habitable zone, such that the liquid water is present here, and also we have a suitable atmosphere which helps for the development of life here. How does Earth form? So the Earth starts from planetesimals. This was explained yesterday by other speakers, how planetesimals forms from the solar system. So now to create Earth, we also need planetesimals. So when many planetesimals comes together and collide each other, they become bigger in size. They slowly grow in size like a planetary embryo or something like this. So ultimately, they grow to the maximum size. This becomes proto-Earth. So you start from planetesimals and you pass through the planetary embryo stage and you end up with proto-Earth. Because you had a lot of impacts of planetesimals also generated huge amount of heat. And also, Earth also contained short-lived radionuclides, the decay of which also produced lots of heat. So this heat melted the proto-Earth almost, the outer part of the proto-Earth is molten. So now whatever nickel and iron, these are very heavier elements, they settled in the interior part of the planet. They went to the core part of the planet and settled. So once you remove nickel and iron, the remaining part of the liquid is silicates. So that makes up the mantle and crustal part of the planet. So once you have this is called planetary differentiation, in which you separate core, mantle, and the crust. So this is happening just within 10 million years of time, less than 10 million years of time. So very quickly it happens. It also happens to the same way for Mercury, Moon, and also for Mars. So these stages are quite uniform between the planets. So once you have a proto-Earth, then what happens? The Earth also underwent a kind of giant impact. It is believed that a small planet like Mars-sized planets collided Earth about 4.5 billion years ago. So when that planet collided the Earth, huge amount of materials came out. Like here you see the small planet collides the Earth. Because of this collision impact, lots of material comes out, and the thrown out debris also goes around the Earth. And through different stages, they also produce a disk. So you produce a disk around the Earth, and some portion of the disk again go back to Earth and collide and accretes into the Earth. So whatever left out beyond the gravity field of the Earth, those materials form the moon. So you produce Earth and the moon. So now what happens to this primordial Earth? So now we want to understand the primordial Earth and how it evolved over a period of time. So when we want to understand Earth, we have to also understand various spheres like geosphere, hydrosphere, atmosphere, and biosphere. We are living in biosphere. We depend on atmosphere and also hydrosphere and geosphere. What happened? Biosphere, atmosphere, hydrosphere, all of them were produced from geosphere activity only. For example, the atmosphere comes out of geosphere through degassing process. So once we produce the atmosphere, the condensation causes hydrosphere. Some of the water goes to the geosphere, they become groundwater. Then life also comes into pictures. So the evolution of geospheres significantly contributed to the evolution of all other spheres. So now let us look at the geosphere. The planet Earth, it has an interior. It has three important layers, as I already explained: crust, mantle, and core. The core mantle boundary is around at the depth of 2,900 kilometers. So now what happens? This entire, the three layers of this Earth is also very dynamic in nature. For example, the upper portion of the Earth is called the lithosphere. This is the rigid part of the upper shell of the planet, which is almost like floating on asthenosphere, like wood floating on water. So the lithosphere is almost floating on asthenosphere, and it moves very easily on top of asthenosphere. And the lithosphere also broken into pieces, plates. So these plates also collide each other. Like here one plate collides onto the other plates, and one plate goes down the other plate. This is called subduction. So this is called plate tectonics. This plate tectonics is facilitated by the asthenosphere here. Otherwise, the plate cannot move on top of it, and the collision also takes place. So the subducted plate also goes down, and it's also going to the core mantle boundary also. So the circulation inside the planet causes a lot of activity, and they also causes the evolution of the planet. To see the interior of the planet, we have to use geophysics. Like for example, when there is an earthquake occurs on top of planets, the seismic waves goes through the planets, and they are reflected by different layers of the planets, and they are reflected back to the surface, and they are recorded. So the velocity at which these seismic waves are traveling inside are captured here. So you can see there is an increase in velocity of compressional waves, and when they reach the core mantle boundary, the velocity suddenly decreased because the outer core is liquid in nature. So this is how the geophysics help us to delineate the interior structure of the Earth. If you look at the temperature also increases from the surface. It goes up to 6,000 degrees centigrade. So all this information comes from geophysics. Now we want to understand the geological evolution of the planet. So how do we understand? If you want to understand myself, my body, I sample a drop of blood and study the DNA and various other biological parameters. Similarly, when I want to understand the planet, I need to sample the rocks. The rocks hold all the information. So if I want to answer the questions, how did Earth form and evolve to its present state? How do I answer? then I have to go to this pile of rocks that are here. So here, the pile of rocks also should have ages ranging from the time of the origin of Earth to the present day, so that you sample the rocks belong to the entire history of the planet. This is very important. Second, the rocks also have three types. One is igneous rocks. The igneous rocks come from magma. So the igneous rocks tells about the magmatic processes that are happening inside the planet. On the other hand, if you study sedimentary rocks, they are forming from the water when it is reacting with the rocks. So it also erodes the rocks and carries the rocks along with the river, for example, river. So the sedimentary rocks are produced by the river, wind. There are many also ice. So these are all come from climatic processes. So atmospheric process, climate process, are all of them are reflected in sedimentary rocks. So by studying the sediments, we understand the climate of Earth better. The third rock is metamorphic rocks. Both igneous and sedimentary rocks like these, they also buried inside the Earth due to many tectonic activity. So when your sedimentary rocks buried goes inside 10 kilometers inside the Earth, they also become metamorphic rocks. The changes as you go downward, pressure and temperature increases, through which the rocks also undergoes changes. Such rocks, when come to the surface again, we can look at them, study what happened at the depth of 10 kilometers. So this is how we understand the processes that took place in the Earth, and we also need the age of the rocks. We have to determine the age of the rocks from the geochronological methods, which was explained yesterday, using isotopic records. So you have parent isotopes and daughter isotopes, the ratio of it, and also the half-life of these isotopes will tell us the age of the particular rock. So when you talk about the history of Earth, we should have a time scale. For example, the Earth born at the age of 4,500 million years ago. That's the origin of the Earth. And we need time scale from 4,500 million years to the present, zero. For example, zero. So the entire time scale is divided into four parts. The oldest one is Hadean eon. That span age from 4,500 million years to 4,000. Then comes Archean, which begins from 4,000 and ends at 2,500 million years ago. Proterozoic starts from 2,500, ends at 541 million years. Phanerozoic starts from 541 to the present day. Same way, we can also have time scale for Moon, Mars, and Venus. If you look at Moon and Mars, the pre-Nectarian periods, they're very equivalent to Hadean and Archean Earth. Similarly, the pre-Noachian and Noachian epoch of Mars is almost equivalent to Hadean. So we can compare the Hadean records of pre-Nectarian Moon and pre-Nectarian Moon of pre-Noachian Mars. Likewise, we can compare one planet to other planet. So this is the map shows the surface of Earth containing ocean floor and the continents. This is where you find all the rocks. The continent contain all the old rocks starting from Archean, Proterozoic, and Paleozoic rocks. Whereas if we go to the ocean, this is very young. It's just formed in the last 100 million years. The Earth crust also broken into a number of plates, like ocean plate, continental plate. So those plates also what happened, they are breaking some places. For example, here it's called a divergent boundary. So they are break and open. Some places two plates collide. For example, ocean plate collides onto continental plate. Here you produce called subduction zone. And some places continent plate collides onto another continent, produce Himalaya. So this is the plate tectonic network of Earth. So what is the oldest rocks we have on Earth? This is the rock called Augusta gneiss. This is found in the northwestern part of Canada. The small piece, the scientists collect it and separate the minerals and study the isotopes composition of these minerals, which gave the age of 4 billion years. So this is the oldest rock we have. But you know that Earth formed about 4.5 billion years ago. So how do we know 4.5 billion years? This is come from the meteorites. Second, some scientists from Australia, they collected some samples from the southwestern Australia. This is the rock called conglomerates. So they powdered and separated a mineral called zircon. This is a very, very strong and highly resistive mineral. This gives the correct age of the origin of this particular mineral. They took this mineral and they determined the concentration of the radioactive isotopes, and they got the age of 4,400 million years. So here it is. They also found ages varying from 4,400 million years to 4,100 million years. This is the oldest minerals scientists discovered from Earth. Interestingly, when the scientists looked inside this mineral, they found some hydrous minerals are inside. When they studied, they found that it is the mineral called muscovite. The muscovite is a mica containing a lot of water. Therefore, when this mineral crystallized, there is lots of water was present at the time. Therefore, we can conclude that about 4,400 million years ago, water was present on Earth. This is another location on Earth in South Africa. There are also rock records also contain zircons like this. People separated and they dated. They got around 4,000 million years age for this type of zircons. Interestingly, these zircon minerals also contained some magnetic mineral inclusions. Look inside this grain. People found few micron magnetite minerals. These magnetite minerals recorded the magnetic field that was present about 4.4 billion years ago. So they found the record that these magnetite minerals inside zircon also showed that Earth had a magnetic field at that time. Even there are other zircon grains also provided evidences that the magnetic field formed about 4.4 billion years ago, and it's almost continued up to 3,200 million years ago. This is very, very important finding because you need magnetic field to protect life on the Earth. You know how important it is. Even the rock records belong to the whole Earth history also preserve the magnetic field memory inside them. This shows that the magnetic field was there throughout the Earth history. So if you want to ask a question, when did the magnetic field form? They formed about 4.4 billion years ago, and it is continuing to be active even today. This is very, very important finding that comes from the rock records. Therefore, whatever life produced in the last 4.5 billion years ago, all of them were preserved in the rock records. You look at Mars. Mars also had magnetic field, but today the global magnetic field disappeared. When did it disappear? About 4,100 million years ago, magnetic field disappeared from Mars. However, whatever rocks that were formed from 4.5 to 4.1 billion years, those rocks preserved the magnetic field that was present at the time. Some volcanoes on Mars also recorded the magnetic field that was present about 4.1 billion years ago. From this finding, we can say that volcanoes were active about 4.1 billion years ago on Mars? If so, on Earth also similar magmatism was there. We can infer. Anyway, Earth has lost all the first 500 million years of geological history. You know, we don't have Archean geological record. We have to look at Mars and Moon. These planets preserve the geological record belong to the first 1 billion years of planetary history. If we look at this geological history, we can say that Earth also experienced huge amount of meteorite impacts in the first 500 billion years of time. Look at the surface of Moon and also Mars. You have huge amount of millions of billions of impact craters on the surface. Second, Moon also have an anorthositic crust. Anorthosite means it's a rock contains more calcium aluminum silicate. These rocks requires magma ocean. Without magma ocean, these anorthosite crates cannot be produced. Therefore, Moon and Mars had magma ocean. If so, did Earth also have magma ocean? Yes, some indications, some evidences are emerging. Look at on Moon, the magma ocean started about 4.48 billion years ago. This magma ocean, it's an ocean, but it's full of magma. It may be the whole Moon is a magma ocean, or only the half of the Moon was magma ocean. We don't know what is the real picture. We know that the magma ocean began its crystallization about 4.48 billion years ago. Once you have a magma ocean, from this magma, minerals also start crystallizing. The minerals that crystallize in the beginning, they are very heavy minerals like iron and magnesium silicates, like olivine and pyroxenes. These are very heavier minerals. Well, they are crystallizing at very high temperatures, and they are also heavy. They are heavier than the surrounding magma, so they go down. They settle on the floor of the magma ocean. Same time, another mineral called plagioclase also crystallizes from the magma, but these are all very light. These minerals goes to the top of the magma ocean, they form a crust like. So this is called anorthositic crust. So this entire anorthositic crust formation took place around 200 million years on the Moon. We really don't know how much time it took on Mars and also on Earth. But we can now presently, scientists believe that magma ocean might have crystallized for a period of more than 200 million years on Earth also. Second, once the planet Earth is crystallized, they become solid on the surface, then whatever happens to the surface that can be preserved. For example, meteorite impacts. So there are hundreds of thousands of meteorite impacts happened on the surface of the Moon, and they produced craters. Why do they happen? Just because of the main belt asteroids, which are sitting in between Mars and Jupiter. You know, yesterday you heard about planetary migrations. So when the planetary migration takes place, these asteroids present in the main belt will also be unstable. They also start moving towards the inner solar system. They go and hit Mars, Moon, Earth, and Mercury. They hit all the planets around 4,000 million years ago. This has happened. This also happened to Mercury. You look at the surface of Mercury, you have hundreds of impact craters, and the population density of these Mercurian craters are very similar to the Moon. So the population of asteroids that produce craters on Mercury and those on Moon, they are one and the same. And same thing also happened on Mars. Therefore, similar impacts should have also happened on Earth also. Therefore, the Marchi and others, they made a model that based on the records from Moon, Mars, and Mercury, they took all the crater population, they put it on the surface of Earth, theoretically, and they found that the entire Earth was covered by full of impact craters. So when the impact happens, it produces a lot of disturbances. It ejects lots of materials. All these materials cover the whole Earth. So about 4,000 million years ago, the whole Earth was covered by impact crater materials, like more similar to Moon. So this is how it is. Then slowly we are moving to Archean time, which is spanning from 4,000 to 2,500 million years ago. So this time of between 4,000 to 2,500 million years record, we only find in these red patches. These red patches are called Archean cratons. These cratons are also there in India, in South India, like Bangalore. You go to Karnataka and some parts of Tamil Nadu, Orissa, also West Bengal. This area has lots of Archean crustal rocks that formed between 4,000 to 2,500 million years ago. These rocks give us a lot of idea about what happened to Earth in those time period. Yeah, look at this map. It tells you so many impact craters formed on the surface of the Earth. So far, we know about 200 craters formed on the surface of Earth, but there are several craters formed, but all of them are eroded. Only we have few tens of them. Some of them also formed during Archean time. So look at this graph shows the impact events over a period of time between 3,500 to 2,500 million years ago. There are many impact events also recorded. They are preserved in the rock records. For example, you go to the Western Australia Pilbara Craton, you look at the sedimentary rock record, people found a lot of impact craters materials are deposited in between several sedimentary rocks. These impact material craters, if you take and see, they have many impact spherules. These impact spherules are very diagnostic, very, very common if you look at impact crater materials. So from these spherules, we can say that impact occurred at that particular time. Then you talk about the continental crust. I still told you about continents. When did these continents form? They formed about 4,000 million years ago. Like rocks called tonallitic gneisses, granites, they all formed in different parts of the continents. Like, for example, Canada, Australia, you go to Indian Shield, also in North America, South America, all these areas, the continental crust is forming just because of magmatic events. The magma comes from the deep interior of the Earth. They come to the surface, and also they come to the crustal level. They produce a lot of a continental crust, something like this. And the granite is a very common rock which formed about 2,500 million years ago. Granites is commonly used in building material. We use for building and all. All these rocks formed about 2,500 million years ago in the continental crust. If you look at the Mercury planets, Mercury also got a lot of volcanism around Archean time. So look, there are the lava flows which are flowing like rivers on Mercury. So similar lava flows also may have flowed on the surface of Earth also. And look at Moon. Moon also have lots of long-lived volcanic activities in the near side of the Moon. Some of the lava flows formed about 3.6 to 7 billion years ago, and they also continue to present up to 1 billion years ago. Even look at Mars. Mars also had a lot of volcanic activity, like time in Archean on Earth. Volcanic activity on Mars is produced by mantle plumes. These are hot floods coming, they're coming from the core mantle boundary. They are originating from the core mantle boundary. They move up, they go and hit the lithosphere of Mars, and they are there for more than 4 billion years. They are continuously heating the lithosphere and produced a very largest volcano in our solar system called the Tarsis volcano. And if you know the continents, the oldest continent that formed on Earth is called Walbara supercontinent. What is supercontinent? We know continent. if you bring many continents together, they become a bigger continent. We call it as supercontinent. One such a continent formed about between 3.6 to 2.7 billion years ago. Some parts of South Africa and some parts of the Western Australia, they came together and they produced a big supercontinent called Walbera. But you know, these supercontinent, they don't be stable. They will also be broken and open. They will be spreading out due to plate tectonics. Here are the rocks in the Indian Shield. In, for example, South India, North India, we have a lot of rocks belong to that particular time. And these rocks give us a lot about what happened to our own crust in the India. And we understood a lot about that. This is one of the oldest sedimentary rocks that we found on Earth. Also in India, the Mazumdar and Chowdhury, they found this sedimentary sandstone from the Paleo-Archean rocks. This suggests that a river ocean was there about 3,500 million years ago in the Indian Shield. Not only here, the whole globe. We have a lot of water. The ocean was there on Earth. Look at Mars. At about the same time, Mars also had liquid water on the surface of the planets. And it also flowed like rivers. You can see the river flows to the crater, impact crater, and it filled it, due to like a lake system. So this has happened around the same time on Mars. Same thing happened on Earth also. If you go to the Mars, you also see oceans. About 3,500 million years ago, ocean was there on the surface of Mars. And you have rivers, you have lakes, and Mars also have delta. Delta, you know, at the mouth of the river and sea, you find this delta. This is the delta on Mars. So Earth also had delta, like this type of delta sediments. So during the Archean time, we have atmosphere, but we didn't have oxygen. So there is no oxygen, but full of carbon dioxide and methane. But water was there, ocean was there. So life like today could not develop because of very poor oxygen level. But still, there are anoxic microorganism also grown at that time. 3.5 billion years ago, scientists found many microorganisms like microbial cyanobacteria. You can see some organic materials. These were discovered from the South Africa. So this suggests that some form of life, the microbial life, started about 3.5 billion years ago. At around the same time, the ocean was also there. Iron also there in the crust. The iron was leached out by weathering process. When water flowed, the iron was removed from the rocks. They went to ocean. In the ocean, cyanobacteria were there. They produce small amount of oxygen. When this oxygen was there, little amount, they reacted with the iron and they produced a deposits called banded iron formations. This banded iron formation was produced in the oceans of Archean time, and this became the biggest source of iron ore that we are extracting today. Whatever iron that we are using, they are coming from the banded iron formation, which formed in the ocean that exists about 3.5 billion years ago. Here is a mines in Karnataka. The Sandur mines is being mined by NMDC. So they exactly mining this type of band iron formation. Not only that, if you come to the end of Archean, lots of collision happens. The crust are broken into pieces, they are all colliding and diverging. So this was happening in South India also. And the plate tectonics was also operating, and there are plates going down and one plate going up. So lots of granites are produced because of this subduction process. So this is what we are seeing. So the granites are produced in South India, like in near Bangalore. If you see Bangalore, you will find lots of granites. If you go to the Karnataka also, you find Hasan area, you find lots of granite. Hyderabad, you find lots of granites. These granites are produced about 2,500 million years ago due to the plate tectonics process. Now we are going from Archean to Proterozoic time. So Proterozoic starts from 2,500 million years ago to 541 million years ago. So this is a very interesting time of Earth history. That's a time the atmosphere, the ocean, they produced oxygen. About 2.3 billion years ago, the ocean and the atmosphere produced a huge amount of oxygen. This is called a great oxidation event. Until then, there was no oxygen. There were very little amounts, but suddenly in the atmospheric oxygen went very high, almost very close to the present day, at least 1/10 of the present day oxygen level it reached. During this time, there are unicellular organisms started blooming in the oceans of Proterozoic Earth. These are some of the examples of fossils people recovered from the Proterozoic oceans. You find there are filamental fossils. These are all cyanobacteria. These are luckily preserved in rocks. And these are the organisms produce oxygen from the respiration. Also, during the Proterozoic time, you produced all the continents. Whatever continents are that you find today, most of them were produced at about 2,500 million years ago. These continents, they were not just keeping quiet. They are coming together like continental supercontinents, and they are breaking open and they are going away from each other. So this is called supercontinental cycles, which happened every 700 million years, 750 million years ago. One of the supercontinents formed between 2,000 and 1,500 million years ago. In Earth, this is called Columbia supercontinent. These continents subsequently broken. And once they are broken by plate tectonics, sometimes the mantle plume also coming from the interior of the Earth goes and hits the supercontinent, and they are broken into pieces. And due to the forces, they move away each other. So they are just almost dispersed. So these planets, the supercontinent is broken into pieces. They are moving away from each other. You look at the planet's position, the continental positions are 1,000 million years ago, and around 900 million years ago, again all the continents came together and assembled. This supercontinent is called Rodina. This is not just story I'm telling. These are based on geological evidences that we get from the rocks. Again, this supercontinent Rodina again underwent breakup. This breakup again opened up, everything opened up, and around 780 million years ago, you can see the Rodina is broken into two parts, and you can see the India is somewhere here. Then around 700 million years ago, the continental situations setup is something like that. And slowly they are spreading. And around 600 million years ago, there is something important happened to Earth that is called Snowball Earth. This snowball, I will explain later. Then again, you see 600 million years ago, the continents are like this, 515 years. Most of them, some of them moved to the northern hemisphere. And finally, about 530 million years ago, you have the assemblage of Gondwana lands. This is a very, very important continental landmass called Gondwana. Now, the whole Earth was covered by ice between 660 and 635 million years ago. The whole Earth was covered by ice. So the planet became cooler. So how do we get this type of situation? It is mainly because of the atmospheric gases. Carbon dioxide, methane, these are all greenhouse gases which heats up the atmosphere. So once you remove carbon dioxide and methane from atmosphere through some process, what will happen? The whole earth become very cold. This is one situation. In the another situation, the sun is also evolving with time. And the sun was also not very powerful like today. So it was very like emitting very less energy. So you have atmosphere and you have sun cycles also maybe playing a little role. And the whole planet was covered by ice. So this is called snowball Earth, or you can say ice cream Earth. So now, this is what happened. The planet also became very quiet. The plates are not moving. Volcanoes are not erupting. When the volcanoes erupt, it throws a lot of carbon dioxide into atmosphere, methane into atmosphere, sulfur dioxide. Then again, they are coming to atmosphere. They will heat up the atmosphere again by greenhouse effects. So this is what happens subsequently. Again, the plates are start moving, and the ice are molten. Again, Earth came back to the previous position. Now, the magic happened to Earth. This was about 530 million years ago. The ocean, you have nice ocean, you have Gondwana lands, and here, both on ocean and land, all life bloomed. Like marine life bloomed, and there's a lot of new life is coming. Invertebrates are coming, trilobites, fish. Fish found about 400 million years ago. They are preserved in rocks like fossils. So this is how the marine life is blooming, and even you find, a turtle, tortoise, and even you have whale. So all these lives are started blooming in the oceans. In the Gondwana supercontinent, you also develop land life, terrestrial life, like you have plant kingdom, and you also birds, and also reptiles, the dinosaurs. All these life forms are developing in the landmass of Gondwana. So this is a very most beautiful period of Earth history where all the life came into picture. But it's not a very simple story. This life also This life also got interrupted by many mass extinction events. There are times where most of the life again killed by some extraterrestrial events or some volcanic eruptions. Lots of life again killed and dead. For example, end of about 4,450 million years ago, about 425, and there are 250 million years ago, 200 million years ago, and also 65 million years ago. Here, mass extinction occurred. That means almost 50% of the species were removed from Earth because this is called mass extinctions. This has happened several times. Now, scientists found around the same time, lots of volcanic eruptions also happened. For example, in Siberia, in the Russian area, you have huge amount of Siberian volcanism that coincide with these young Permian mass extinctions. Also, if you look at the 65 million years ago, you have very big impact event called Zixloop impact events that occurred in the Mexico country. Here you have an ocean and continents where a 17-kilometer diameter projectile meteorite came with a velocity of around 12 kilometers per second and hit the Earth's surface, and it produced a big crater like this. So this is around 170 kilometer size crater was produced by this meteorite impact. So what happened at the time? So from the crater, huge amount of material comes out, vapor plumes comes out, carbon dioxide, sulfur dioxide, all of them are removed. They are released to atmosphere because of huge amount of heating. At the time of impact, the temperature reaches of the order of 3000 degrees centigrade. The rocks are molten and they're vaporized. and goes to the entire atmosphere of Earth. So the whole atmosphere is present. Also, the dust particles covers the whole Earth. So the sunlight doesn't enters into atmosphere. It doesn't reach the surface. So no sunlight for months, no photosynthetic activity. So there is no life. Plants cannot grow, and global fire also happens. So this is called. So this is the one particular impact is believed to have caused the removal of dinosaurs. For example, just imagine the impact itself disrupt the whole crust. Even you can see the effect of impact even at a depth of 40 kilometers. So this is the kind of, this type of impacts occurred on Earth in alien time. Millions of craters occurred. Even there are several craters occurred even later. So the impact events brings lots of catastrophe to the planets. Anyway, this is the Gondwana land that was there at about 500 million years ago. And this supercontinent cannot keep quiet. They also fight each other, it seems. They broke into pieces again due to some underlying activity, earth activity, like some kind of plumes. They comes and hits it, and they also break them into again number of plates. These plates also start moving away from each other. So this Gondwana land, Gondwana supercontinent, slowly became Pangea supercontinent about 200 million years ago. So this was the continental assembly, which was there about 200 million years ago. So now, again, this is hit by some mantle plume activity or several other processes. Again, these continents are broken into subcontinents. They also started moving from away from each other. And you look at our own Indians, this is the India about 60 million years ago. And they also started moving, going towards the Eurasian plates like this. So they were going like this and started rotated counterclockwise 30-degree. They collided onto Eurasian plate and it produced a huge Himalaya. So this is how the India subcontinent moved and slowly collided onto the Eurasian plate, and it produced a huge mountain belt. In this process, the Indian lithosphere also gone beneath the Eurasian plate, subducted beneath. You can see here the right side, one plate gone down. This is Eurasian plate, this is Indian plates. So this is how the plate tectonics played a havoc to the planet Earth. So if you see plate tectonics, when it starts, this is around 2.5 billion years ago. Some scientists believe that it happened even before, but it was there in some form or other. But plate tectonics became very prominent in the last 2000 million years ago. This is how the plates are today. You are India here, and you have Asian plate, you have Russia, here you have African plate, North American plate, South American plate, Australian plates. These plates, even it is not quite now, this also start moving away from each other. We don't know, after 300 million years or 500 million years, again, there will be another supercontinent may be formed. Why not? So when these plates are moving across each other, they also produce lots of seismic activity. If you look at the earthquake map of Earth, you find that millions of thousands of events are occurring along the plate boundaries. This is mid-oceanic ridge. You can see the earthquakes themselves define the plate boundaries. You can see here. And this is Himalaya. That's where continent-continent collision occurred. So these are the chains of plates. You can see the swarming of lots of earthquakes. Look at our own India. You can see lots of, almost thousands of seismic activity. Earthquakes are happening all the time. And if we see, most of the earthquakes are occurring in the Himalayan region and also in the Andaman region. Why? Because that is where two plates collided just very recently. Recently means just 5-10 million years ago. They collided and still they are adjusting each other. They're hitting each other, produce large amount of earthquakes. Therefore, these regions are very hazardous to earthquakes. That's why, the earthquakes that occurred in the Nepal was devastated. Similarly, any part of Himalaya is very vulnerable to earthquakes. These activities are caused by faults. There are some weakness planes in the earth crust. They move up and down here and there. They produce lots of earthquake activity. Moon is also seismically active. The Apollo, when they went to Moon, they also installed 4 seismometer on the surface of Moon. They also recorded 28 moonquakes, which are very similar to earthquakes. But here, earthquakes don't show like plate boundary earthquakes that you see on Earth. Here, earthquakes are occurring very randomly. Earth also experiences many other type of earthquakes like deep moonquakes, artificial impacts, wherever you hit. For example, when Chandrayaan-3 landed on Earth, it should have generated some seismic activity. Even the meteoric bombardment also produced huge amount of seismic activity. Look at Mars. Mars is also seismically active. The NASA put a seismometer about 4 years ago on the surface of Mars, and it operated for about 4 years. But during this time, more than 1,300 Marsquakes were recorded by the seismometers, out of which some of them are very similar to the earthquakes that we occur on Earth. So these Marsquakes, you can see they're occurring along the active fault regions, but they don't show something like plate boundaries. So you don't have plate boundaries on Moon and Mars. Therefore, you don't have plate boundary earthquakes in these planets. Yes, now we come to today. The problem is global warming. It's all come from carbon dioxide, carbon monoxide, sulfur dioxide. All of them are coming from the emissions from the vehicles, factories, and carbon dioxide content was about less than 300 parts per million around 1960. Now it increased to more than 400 ppm. So this addition of 100 ppm more carbon dioxide caused global warming. This global warming caused approximately 1 degree centigrade rise in global temperature, which caused melting of polar ice, and it also caused extreme weather. Like, sometimes you receive 30 centimeter rain in one day, like what happens in Chennai, Bangalore, also what happened recently in Dubai. So these things we never heard about 50 years ago or 160 years ago. So now we are start experiencing like a huge extreme events. All come from carbon dioxide. Now let me summarize the Earth history. Now you understood how Earth evolved from the beginning and how it evolved to the present day. During Hadean time, the Earth was just formed and the crust is very juvenile, very hot. Ocean just formed, atmosphere just formed, but there is no oxygen. Lots of meteorite impact occurred at the time. The Magma ocean was there. From the Magma ocean, crust was forming. Then it comes to Archean. The continents are start forming. Ocean is continuing to be there. Atmosphere was so full of carbon dioxide and methane. There are some micro life was there, and they are there here and there. Then when you come to Proterozoic, the supercontinents happened. Supercontinents are formed, broken. Many times they are adjusted themselves. Ocean became very microbial life became more blooming to the next time. And atmosphere also become more rich in oxygen around 2.3 billion years ago. And that oxygen remained in the atmosphere all the time. And if you look at the last 30 million years, the oxygen even become even more. So this is the very unique planet in which oxygen was blooming around the Proterozoic time. And life, the wide variety of life came into existence about 550 million years ago. The life became, the wide variety of life came into existence. But again, you have a lot of many mass extinctions that killed lots of life. So there was a great dying was there in Earth. So slowly you come to the plate tectonics, Gondwana land, break up. So again, Indian plate came and hit the Eurasian plate. India was produced, Himalayan belt was produced, and we have global warming now and many other things. If you look at Mars, Mars is not so like that. We look at, and Mars, you have large amount of impacts were there in the beginning. Magnetic field was there only for 400 million years. Large impact, light heavy bombardment was there in the first 6-7 million years. Was there, volcanism was also there on Mars, but the quantity, the intensity decreased with the time. And Mars also had ocean. The rivers were active. They also flowing lots of water. But when you come to the recent time, all water gone. And this is how Mars. If you look at Moon, this was also not there. Just impact and impact, some volcanism, some tectonism, some. So this is how our inner planets and Earth is luckily very unique. That's why we are here to speak about it, to hear about it. So